Welcome everybody, and I'd like to ask Francesc to continue his course on the Iwasawa theory of elliptic curves at Eisenstein primes.
Yeah, thanks very much for the introduction. Yeah, so let me begin by recalling what we saw yesterday. Yeah, the setting was we started off with an elliptic curve over the rationals, conductor n. We fix P any odd prime of good ordinary reduction for E. And then for a suitable imaginary quadratic field satisfying the Wegener hypothesis, and for the last part, also we needed P to split in K, we introduced three different main conjectures. One was the classical Iwasawa main conjecture of measures. And we saw that if that was knowing the main conjecture would imply the P part of the BSD formula in rank 0. Then we introduced Perrin-Rieux's main conjecture, which has to do with the anti-cyclotomic CP extension of K. And then we saw how this main conjecture then implies what we now call the P converse to the theorem of Haruzo and Kolyvagin. And lastly, we introduced this what we call the BDP Iwasawa main conjecture. And the very last thing we saw yesterday was that this main conjecture implies the P part of BSD formula in rank 1. But as we saw at the very end of the argument, first one's proof the result in rank 1 over K, and then to descend and to Q, one needs to know the P part of the BSD formula in rank 0 for the quadratic twist. Okay, so the BDP main conjecture by itself doesn't quite imply this. You also need to know the case of rank 0 for the quadratic twist. Okay, and so that's a summary of what we saw yesterday. And then at the end, there were some questions of these conjectures that we introduced for any good ordinary prime. In these lectures, we're going to focus on the case of Eisenstein primes, but people were asking what was known in more generally. So I can include here a bit, see if I can make it work. Okay, that didn't work. I was hoping. Okay, no, so I have to write it. Okay, so yeah, so let me write here. Okay, so when the Galois action on the P torsion is large, okay, so in particular, when the P torsion is irreducible as a Galois module, so not the case that complementary to what we're looking at here. Then these three main conjectures they are now under mild ramification hypothesis. On this Galois module. Okay, and these results were obtained by blending essentially two. Well, so proving the two divisibilities, each of which require different kind of techniques. Okay, so on the one hand, one had the method of Euler and Kolyvagin systems, so Euler / Kolyvagin systems. Okay, mostly developed by Kato in this context and Howard, the anti-cyclotomic one. And then on the other hand, the other divisibility was obtained by a vast generalization of Rivet's method, as seen in the lecture series by the same Rivet's method that we are seeing in Samit and Mahesh's lecture series. Okay, so a vast generalization of Rivet's method. Okay, more precisely, so maybe here the key names are Skinner-Urban in the case of Mazur's main conjecture, and Shin-1 in the case of the other two. Okay, so here this was for the group GU22, here is for the group GU31. Okay. All right, so now from now on, we are gonna restrict to the case of that was up until recently, the case when the p torsion is reducible. Okay, so from now on, we suppose the p torsion is reducible. As GQ module. Okay, so we can write its semi-simplification as the sum of two characters that I'll denote phi and psi. Okay, so here where phi and psi are characters of the Galois group of Q valued in Fp cross. And of course, the product will be the mod P cyclotomic character. Okay, so we know that phi times psi it's omega, the Tegmirror character. Okay, so here is today's goal. Okay, so the goal is to explain the proof of the following theorem. I'll call it Theorem A. Okay, with its joint work with Giada Grossi and Chris Skinner. Okay, so we're going to suppose it's in this setting we have above, and we suppose that certain assumption on the character phi. Okay, so suppose phi restricted to a decomposition group at P is different from 1 or omega. Okay, where as mentioned this GQP denotes a decomposition group at P. Okay, and then we take an imaginary quadratic field. Imaginary quadratic. Such that we're in the situation of the BDP main conjecture. Okay? Namely, we need the Hegener hypothesis and also P to split in K. Okay, so under this in this setting, then we can show that this Iwasawa module that appears in the BDP main conjecture is torsion over the anti-cyclotomic Iwasawa algebra. And its characteristic ideal has the generator predicted by the conjecture. Okay, so with characteristic ideal, remember we need to extend scalars because that's where the BDP p-adical function lives. Okay, so this characteristic ideal is generated by the square of BDP. Okay, and hence the BDP main conjecture holds. Okay, so that's this is a theorem I hope to explain today. Are there any questions about anything so far?
Only previously.
I'm sorry?
Jehundi was also involved when some.
Yeah. So there is part of this result was in obtaining joint work with Jae-Hoon Lee, and once I get to the proof, I'll mention what part of this was obtaining that previous joint work. Any more questions? Okay, so okay, so now, so the proof is going to go in 2 steps. So the proof is in 2 steps. Okay, so first we're going to show that this XV, this is indeed lambda torsion, and we're going to prove one of the divisibilities predicted by the conjecture. Okay, so this is lambda torsion. With a divisibility, namely characteristic ideal divides the periodical function. Okay, so this is this divides the periodical function Okay, and this yeah, I see a question in the chat. I'll look at it in a second. Okay, but let me first say that, so we're going to prove this divisibility, but because we are in this reducible case, the best we can hope for is to get a divisibility after inverting P. Okay, and let me address the question in the chat. So if these results 1, 2, and 3 true for elliptic curves over totally real field scale? Yes, so so certainly this theorem A, I think, yeah, this should be accessible also in the totally real field case. Yeah, it's not written down, but it's certainly within reach. The techniques that we use seem to be also available in this marginal setting. Okay, so yeah, first we're going to prove a divisibility, and so we've seen in Samit and Mahesh's lectures, and also Antonio mentioned it, that in classical Iwasawa theory, because we have the class number formula, if you want to prove an Iwasawa main conjecture, it suffices to prove one of the divisibilities. Now, in our case, in the setting of elliptic curves, the analog of the class number formula, or the counterpart, as we've seen in Matthias' talks, for example, would be the VSD formula, which is kind of the application we want to deduce from proving this main conjecture. Okay, so we have to do something else in this setting to get from this divisibility the full conjecture. Okay, and one way to get there is combining this with an understanding, or rather an equality, of the Iwasawa invariance on both sides. Okay, so what we're going to do next is exploit the congruence that we have. Okay, so mod P, our representation is the direct sum of 2 characters, so it's reasonable to hope that we might use this to relate what we are trying to understand about T to something having to do with the character. Okay, so to show Okay, so concretely, what I will be able to show is that this Iwasawa module and the p-adical function have both mu equal to 0. Okay, so mu here, for those who haven't seen this before, is just, so you can view, you can attach to each of these two objects a polynomial, characteristic polynomial, and mu equal to 0 means that they are not divisible by p. Okay, and then the degree of this polynomial is what we call lambda. So we're going to show that both have mu equal to 0 and have the same value of lambda. And the same lambda invariant. And now, if you show that mu is 0 for both, this ambiguity that you carry over from this divisibility is harmless. And then once you have the equality of lambda, you get theorem A. Okay, so that's how the proof is going to go. In fact, we're going to do the steps. I'll explain them in the reverse order. So let me move that down here. And change the numbering. Okay, so these are the steps of the proof. First, let me begin with the first one. Okay, so for which what we're going to do is extend a method introduced by Greenberg and Valsal in the cyclotomic setting. Okay, so what we're going to do is develop an anti-cyclotomic counterpart of the method. Anti-cyclotomic Greenberg-Valsal method. Okay, so the hypotheses are throughout will be, unless I say otherwise, the hypothesis will be we're working in this setting, the setting of theorem A. Okay, so what I'm going to do is I'm going to let sigma denote the set of primes of K dividing N and P. And then I let S denote those primes in sigma different from P or not away from P. Okay, and we consider the following S in primitive Selmer group. Okay, so it's going to be, I'm going to just repeat the definition I gave yesterday, but I'm going to drop the condition at the primes in S. Okay, so this will be, by definition, the kernel. And I'm going to write H1 of this group, the Gala group of this extension, with coefficients in EP infinity. And now I'm just going to have the restriction map at V bar. Okay. That's what we call the S in primitive Selmer group. Okay, in fact, so then I'm going to let X Vs E K infinity minus to be similarly as we were doing before, the Kolyvagin dual of this guy. Okay, and we're also going to need a residual counterpart of these objects, what we call the residual Selmer group. Okay, so let me write cell B, and now the coefficients will be in the p torsion. Okay, so I'm just going to copy the same thing, but the only thing that's changing here are the coefficients. Okay, so coefficients are now the p torsion, and it's reasonable to look at this subject because we want to exploit this. Okay, so all right. Okay, so this is what we call the residual thermal group. Okay, and then I'm not sure if I'm going to need this, but let me write it for the Kolyvagin dual. Okay. So we're going to look at this in primitive and Selmer groups. And now, what's the basic principle underlying this method? Okay, so the basic principle is that the main conjecture we are interested in, or the equality of characteristic ideals we're interested in. Okay, so this one here. Should be actually equivalent to their S in primitive analog. Okay, so this is equivalent to the characteristic ideal of this S in primitive Selmer group being generated by an analog of, okay, so an S in primitive counterpart of this BDP p-adical function. Okay, so this p-adical function has a certain interpolation property that I didn't write down precisely, but I told you what L values were being interpolated. This S in primitive one will have the same interpolation property of the same L values, but these classical L values, they will be of the L function with the L factors at the prime sin S being removed. Okay, so you can think modally of this S in primitive as the p-adical function, the original one, but with the Euler factors in S removed. Okay, so this modally, what we're doing is removing the Euler factors. I guess. At B in S. But now, what's the advantage of this reformulation, if you want, of the problem, is that this second one is actually better behaved with respect to congruences. Okay, so the advantage is that this is better behaved with respect to congruences, mod P. Okay, and in particular, it will be for these S in primitive objects that we will be able to determine their mu and lambda invariants in terms of information modulo P. Okay, so here having to do with the P torsion Galois module, and here having to do with the reduction mod P of these functions. Okay, so that's the principle that we need to kind of execute. And wait, are there any questions before moving on? Okay, so here is the first proposition. Okay, so suppose same hypothesis as before, phi restricted to GQP is not 1 or omega. Okay, so then our Iwasawa module is lambda torsion for the S in primitive 1. Okay, with mu equal to 0 and lambda equal to 2 lambda invariants associated to phi and psi. Okay, so this will be introduced in the proof. Okay. Okay, I will tell you exactly what they are. Okay, so yeah. Okay, so proof. Okay, so first of all, let me set up some notation. Okay, so we have this character phi, which is a mod p character. Now I want to view it as valued in ZP. Okay, so I'll just compose with a take mirror lift. Okay, this is our phi, and I'll denote phi tilde this composition. Okay, so then by standard arguments, essentially due to Greenberg, what you can show is that the following Selmer group. Okay, so I'll denote it cell VS P tilde K infinity minus. Okay, I'm just going to repeat the definition I gave for the primitive Selmer group for E, but now for this character. This is going to be the kernel H1 K sigma K infinity minus. Now we consider QP mod CP with the action given by this phi tilde we just introduced. And this going to H1 K infinity P bar QP mod CP. Okay, so and if the inflation restriction argument will allow you to identify this with the dual, the Holmes, from a certain Galo group. I'll denote M infinity. This is an extension over K infinity K phi. Okay, so the Kolyvagin dual of this Galo group. Okay, so if you want, I can tell you what this is. Okay, so this group here, is a Q bar fixed by the kernel of phi restricted to GK. And now this is the maximal abelian pro P unramified outside V and S. Okay, so it's the maximal such extension of the compositum of K infinity and K phi. And these standard arguments I'm alluding to, well, first you get this isomorphism, and also you show that this is lambda torsion with no proper finite index lambda minus some modules. Okay, so with no proper finite index lambda minus some modules. So this is pretty standard. Okay, but on the other hand, we have for this character, for this anti-cyclotomic, over this anti-cyclotomic extension, we can invoke the results of Rubin and Hida. Okay, so by Hida and Rubin, what we know is that this same Selmer group has vanishing mu invariant. Okay, so let me call it mu invariant mu phi. Okay, we know it's 0. Okay, but it has mu invariant 0, so that means it the dual has finite p torsion. But from the previous step, we get that this p torsion has to be trivial. And therefore, what this says, since the Kolyvagin dual has no p torsion, that means that this group is divisible. Okay, so what we get is that cell Vs phi tilde k infinity minus is a divisible group. Okay, so say isomorphic to a number of copies of QP mod ZP, and the number of copies is nothing but the lambda invariant of this character, the anti-cyclotomic lambda invariant. Okay, that's the lambda phi we have in the statement. Okay, but now once you have this description, you can compute lambda phi by just taking p torsion. Okay, so this implies that this lambda phi is, we can find it by just computing the FP dimension of the p torsion of this module. Okay, but now one of the uses of the hypothesis we have on phi is that this p torsion is the same as the analogous in primitive Selmer group for the original phi. Okay, so in some sense you can bring the p torsion inside. Okay, so this is the same as cell Vs phi over k infinity, which is by definition the same Selmer group as before, but it's residual counterpart. Okay, so now the coefficients are Fp with action by phi, and we do the same. We take the same kernel. Okay. But now we are basically done, because from this, using this divisibility, you easily get the following exact sequence. Okay, so okay, so relating this residual Selmer group for the character, and the residual Selmer group for our elliptic curve. Okay, but now in this exact sequence, the flanking terms, we know they are finite by this result of Hida and from the work of Rubin and Hida. Okay, so these are finite. By Hida and Rubin. Okay, and therefore the middle term is finite as well. But being finite, okay, so yeah, maybe I should add here. Okay, so this is going to be the same as, okay, the same hypothesis we got on phi will allow us to show this isomorphism, similarly as we had over here. But now saying that this module is finite means precisely that this module is a lambda torsion with vanishing mu. Okay, so this implies that XPS ek infinity is lambda torsion with mu equal to 0. And moreover, we can read off its lambda invariance by computing the dimensions of these as FP vector spaces, and we get that, yeah, and so the lambda of the Selmer group is the sum of these two invariants. Okay, so that's basically the argument. Okay, any questions about this?
A question.
Yes.
At the bottom of the left-hand page, you said you wrote no proper finite, but you said no proper finite index. Does that make sense?
That's, yeah, great. Thank you very much. Thank you very much. Yes. Yeah. So if I was doing I was looking at the dual, we'll be saying that there are no proper finite lambda submodules. But yeah, for this original one, I said the right thing and I wrote the wrong one. Thanks a lot. Any more questions or comments? Okay. All right. So we have this result about the Iwasawa invariance on the algebraic side. On the analytic side, there is a similar story. Okay, so on the analytic side, we have this isomorphism, which easily implies that the new form associated with our E is actually congruent mod P with an Eisenstein series. Okay, so we get that F, the new form associated to E, is congruent to something I'm going to call maybe E psi. So it's a way to Eisenstein series. And it's a congruence mod P. Okay, and for this, Daniel Chris wrote a very nice, it's a very nice paper where he deduced from this congruence a congruence between the VDP p-adical function on the left-hand side and a product of two cat p-adical functions. Okay, so, and again, this involves the S in primitive versions. Okay, so this is congruent to a product of two cats, anti-cyclotomic cats. Okay, so this is mod P lambda to the inverse. Okay, where these are cats p-adical functions. Okay, so again, this congruence now, because we know from Hida's work that these p-adical functions have vanishing mu. The congruence implies that so does the VDP. And now, because we have vanishing of mu, from this congruence, we can also read off, we can compare the lambda invariance by looking at mod P. Okay, so we get that the lambda of this guy is the sum of the lambda invariance of the other two. Okay, but now with these equalities we have here, if we combine them with what we did on the algebraic side is that by proposition 1, we know that the lambda of XVS E over K was what I call lambda phi plus lambda psi, and we saw that mu was 0. Okay, so it just remains. So we already know both have vanishing mu, the algebraic and the analytic side, and Rubin actually tells us implies in particular the equality of the lambda invariant. Okay, so we get what we want. Okay, we get step 1 in the proof. Okay, so this concludes step 1. Okay, which was this comparison of Iwasawa invariants. Okay, so any questions about this? All right, so now, if not, this now reduces the proof of we are reduced now in this proof of theorem 2 to proving this divisibility. Okay. All right. So that will be the second and last step. Okay, and for that, we're going to do a Kolyvagin system argument. But with error terms. Okay, so right. So let me state this as proposition 2. Okay, so suppose, so this is more general. We don't need to be in this reducible case, but somehow the new case is a reducible case. Okay, but all we can assume on the Galois image is that there is no p torsion defined over K. Oh, sorry, I'm going ahead of myself. So yeah, this is not the Kolyvagin system argument. It's something we're going to use later. Okay, so under this hypothesis, we can show that the following are equivalent. Okay, so one is that the BDP Selmer group is lambda torsion. And we have a divisibility in, say, this direction. Okay, taking place in lambda tilde minus with p inverted. Okay, so that's equivalent to okay, in other words, this Selmer group that appear in Per-Henrius conjecture. It was the usual Selmer group up the anti-cyclotomic tower. And so remember, in this case, this is conjectured to have lambda rank 1. And we have this divisibility, but the characteristic ideal of the torsion part divides the characteristic.
Sorry, maybe I missed some stupid something. What is lambda tilde?
Yeah, the lambda tilde is just lambda, but you, instead of looking at the Iwasawa algebra with coefficients in ZP, you look at, you take the one with coefficients in ZP and ramified. So the maximal, the ring of integers of the maximal and ramified extension of QP. Okay. So it's just you can just take lambda minus if you like, but yeah, I'm keeping track of this scalar extension. Okay, so okay, so this is equivalent to this. Okay, so these two statements are equivalent, and one can actually take the opposite divisibilities in the same call. Okay, so same. The same holds for the opposite divisibility.
On the left-hand side, you want to take the torsion part?
Yes, thank you. Thanks, Janko. Yeah. Okay, and the same holds for the divisibilities. The opposite ones. Okay. And I think to be really precise, I should also say, I should add the condition that this is non-zero. And here I should add the condition that this is not lambda torsion. Okay. All right. So I'm going to be very brief on this. I'll just tell you what's the key point. So the key is a link between this lambda-adic cohomology class and this p-adical function. Okay, okay, and the link is something that we've seen in Antonio's lecture, for example, in the context of cyclotomic units. Okay, so in this context, we have kind of a lambda-adic BDP formula. Okay, and join what we share. So what this says is that there exists some generalized Kalman power series map, or a big logarithm map, if you like. Called V. It's a map on the local Iwasawa cohomology. With coefficients in TB. An injection into lambda minus. Okay, let me write tilde. Okay, with finite cokernel. With the property that it sends the restriction at V of this lambda-adic Heegner class to the BDP p-adical function. Okay, once you have that, it's just standard arguments using global duality will give you the equality of these two statements. Okay. Any questions about this? Okay, so now I can state the Kolyvagin system argument that I was about to write. Okay, so now everything has been reduced, as I'm going to explain, to the following proposition 3. Okay, so remember, we've shown equality of Iwasawa invariance. So now all it remains to do is prove this divisibility. What we're going to do instead is prove a divisibility on this side, and then use the equivalence to get what we want. Okay, so the divisibility we're going to show is the following. Again, suppose there is no p torsion defined over k. Then X, the usual thermal group, k infinity minus, has lambda rank 1. And we have a divisibility after inverting p. Okay, so the torsion submodule divides the characteristic ideal of the index of the Heegner class. After inverting p. Okay. So the proof, let me say a few words about the proof. Okay, in fact, the proof of this result is one of the key technical advances in this work. Okay, so it's going to be a refinement of Kolyvagin's methods. Applied to the Euler system of Heegner classes. Okay, and because we have shown that the p-adical function is non-zero, that gives a way of showing, of deducing that this class is not lambda torsion. So there is a non-trivial input to start off the argument. Okay, and so the difficulty in this refinement is that we're having making a very weak hypothesis on the image, on the Galois image. Okay, so the main difficulty is that we're making no big image hypothesis. Okay, so let me try to tell you roughly how the argument goes. Okay, so first of all, by standard arguments, as developed by Howard, standard arguments. What you can show is that once this lambda-adic Heegner class is non-torsion, the thermal group has lambda rank 1, and up to pseudo-isomorphism is of this form. It's a copy of lambda minus direct sum with the sum of two equal modules with m minus a finally generated lambda torsion module. Okay, so that the torsion part breaks up as a sum of two equal pieces is a consequence of a generalized Castle state pairing that one can define in this setting. Okay, so what we want now is to get our hands on the characteristic ideal of this M, should be divisible by the index. Okay, so we're going to do it as usual, working at a height 1 prime at a time. Okay, so, and we are working away from P, so let's take frag P to be a height 1 prime different from P. And we take a sequence of height 1 primes approaching our given prime as M goes to infinity. Okay, so we can think of these height 1 primes as giving us characters on gamma minus. Okay, so each of these P's of M correspond to a character from gamma minus to some finite extension of QP, some finite extension of ZP, let's call it R. So this is finite over ZP. Okay, so then from a Chebotarev argument, okay, so this Chebotarev argument, you do it, to inductively choose a sequence of so-called Kolyvagin primes. Okay, so to inductively choose sequence of Kolyvagin primes. Okay, so these are Kolyvagin primes. They mod p to the k, and you're going to take k to be sufficiently large. Okay, so let me say depth k Kolyvagin primes, and k we're going to take it sufficiently large. Okay, so you run this argument, and what we get is that the length with respect to this prime of our torsion module M localized at this ideal is less than or equal to the length of the right-hand side. So let me just denote it as check PM. We understand what it means. Okay, so we get this plus some error term, E sub M, with error term E sub M, which is it's some multiple. So this is roughly the p-adic valuation of this character alpha M evaluated at gamma minus its inverse evaluated at gamma. Okay, so it's roughly this, which as M goes to infinity, this order is bounded as M goes to infinity, unless, okay, so this is O of 1 as M goes to infinity. But there's a case where this is certainly not true, namely when we take this P to be the augmentation ideal, in which case these characters would be approaching the trivial character. And for the trivial character, this difference would blow up. Okay, so this error terms remains bounded unless we are dealing with this height 1 prime. Okay, the augmentation ideal. Okay, so if we stay away from this prime, what we get from this inequality plus a control theorem is that the length at our fixed chi1 prime p, the one we pick over here, is less than or equal to the length S check K infinity Heckner. Okay, but all provided p is different, is not the augmentation ideal. Okay, and so now what do we do to handle this case? Okay, so for that, which we can think of, we can identify with T if we view lambda as a power series in T. Okay, so for this, we take, well, the obvious sequence of prime approaching this ideal. Okay, which now this correspond to characters alpha M, which are congruent to 1 mod p to the m. Okay, so this will give us a character in CP cross, alpha congruent to alpha M, congruent to 1 mod p to the m. So now what we need to do, we need to choose Kolyvagin primes differently from before. Okay, so we choose Kolyvagin primes. Again, of depth k with k sufficiently large, but we're going to choose them. So these Kolyvagin primes are in particular primes which are inert in k. Okay, so the Frobenius of these primes is complex conjugation. The Frobenius of k over q is complex conjugation. So in order to choose these Kolyvagin primes, one needs to work over some extension of q on which there is an action of complex conjugation. Okay, and in working with this first type of primes, that's for an arbitrary character, the action of complex conjugation takes alpha m to its inverse, and that explains the appearance of this error term in this case. Now, in this second case, what we're going to do is exploit this congruence that we have mod p to the m. That then gives us that if we look at the p-adic representation twist by this character, the complex conjugation doesn't act on the twist, but it acts on the twist mod p to the m. Okay, so we're going to use this observation to choose to get this different way of choosing our Kolyvagin primes, and then run an induction argument again, which will be of a different sort than in the previous case, but still it can be made to work. Okay, so we choose Kolyvagin primes by working. I see I'm already out of time, so I'll finish very soon. Just 2 more minutes. Okay, so we work on TP of the tensor alpha m mod p to the m, and explore the fact that complex conjugation acts here. Okay, and we do a new induction argument. That will give us the missing inequality of length. Okay, so for this now we get, after running this induction argument, we get this inequality of length over ZP with an error term that now will be independent of m. Okay, and then so they give us the inequality of length also for the missing one here, and therefore we get the divisibility after inverting. Okay, and in response to Ashay's question at the beginning, yeah, so the first part of the argument, this Kolyvagin system argument, was done in a previous joint work with Yada Grossi, Chris Skinner, and also Jai-Fun Lee. Okay, and it's in this in a more recent work with Grossi and Skinner that we have come up with this argument that allows us to handle the case of the augmentation idea. Okay, and since I'm already out of time, I can say so now combining the 3 propositions, we get the proof of Theorem A. Maybe right here. Okay, so proposition 1 through 3 imply Theorem A. And I'll finish with a remark. Okay, so here we have proved, yeah, so what was Theorem A? Okay, so we have shown this, this BDP main conjecture as stated, and in the previous work we can prove it after in lambda tilde minus 1 over t. Okay, so for the arithmetic applications I mentioned yesterday, having this having to divide T is harmless if you are interested in a situation where the Selmer rank over K is 1. Okay? Because if the Selmer rank is 1, then that's telling you that T doesn't divide either side of this divisibility. So it's as good as if you had the equality. But for the application to Mazur's main conjecture, which is what I want to talk about tomorrow, we're going to exploit crucially the fact that we have this theorem A holding integrally over lambda, okay, covering all high components. Okay, so I'll just mention that equality in lambda tilde minus 1 over T is enough for arithmetic applications to e-converse of Grosjean and Kolyvagin and P power of DSD in rank 1. Okay, but theorem equality in lambda tilde will be essential to the proof of Mazur's main conjecture. Okay, so these applications were in case of this divisibility was joined with Grossi, Lee, and Skinner. Okay, so yeah, again, I'm sorry for running, taking a few more minutes, but I'll stop here. Thanks. Thanks for listening.
Thank you very much for your talk. There's a question in the chat.
Yes, I see it. So they're asking if the BDP p-adical function is constructed using p-adic interpolation. And yes, it is. I think I stated roughly what the interpolation property was yesterday. So it has this interpolation property over here. Okay, so it interpolates these twisted values. Oh yeah, okay. That Egnat is asking whether the arguments are simpler if the p torsion is not split. In fact, our arguments only care about the semi-simplification. So maybe if one knew that the p torsion was a non-split extension of these two characters, maybe. So yeah, so here one condition we have on this theorem A, if I go back here, is this condition. This we want C to be different from 1 or omega. I think it would be very interesting to remove this hypothesis, and it's conceivable that in order to handle these cases, maybe for some arguments, assuming that you have a non-split extension might be useful.
Are there further questions, comments in the audience?
These Selmer groups that correspond to the BDP ones, these are torsion. I guess one
Yes.
can also define these type of Selmer groups for the ZP squared extension. And
That's
then
right.
my question is like, do you expect an MHG type conjecture for this setting, like from anti-cyclotomic to the ZP squared extension?
If I expect what, sorry?
An MHG type conjecture.
What type of conjecture? An Iwasawa main conjecture?
No, it's an MHG conjecture.
Sorry, I'm not getting the word.
Okay, thank you.
What? No, sorry, can you repeat? What type of
It's
conjecture?
MHG conjecture.
This is a
MHG. Oh, okay. For in non. Okay. Sorry, I'm not familiar with non-commutative Iwasawa theory, but certainly one can define an Iwasawa, one can define this BDP Selmer group over the ZPIC square extension, and one can formulate maybe a commutative main conjecture over this ZPIC square extension, and that's actually something that I'm going to mention tomorrow. Okay, so I mentioned here at the very end that we're going to exploit this equality we have shown of an anti-cyclotomic main conjecture, and we're going to use it to deduce something about cyclotomic Mazur's main conjecture. And the way we're going to be able to go from one to the other is by viewing everything inside the ZPIC square extension of K.
Thank you.
Yeah.
You mentioned this standard argument, Howard.
Yes.
Two copies of
Howard?
M. Two copies of M appear. Can you just say maybe it's standard?
Where was it? Here? This part?
Yes.
Yeah. So so here I said, so yeah, showing that this is lambda rank 1. Well, so yes, so there are two parts here. One is showing that this has lambda rank 1. The other is that the torsion submodule decomposes in this form. So that this decomposition holds, as I briefly mentioned, it follows from, because we are in this anti-cyclotomic situation, we can exploit this conjugate self-duality, Howard did, to define a generalized causal state pairing on the Selmer group.
Okay.
That allows you to show that the torsion part will have this structure. And then to have the rank one needs to develop kind of a weak form of the arguments that go into this divisibility, this induction argument. But it's just a weak variant of it is enough for you to conclude having lambda rank 1. That's why I said it's kind of standard.
Okay.
Yeah, I should say that. So yeah, when there is a big image hypothesis, you can choose all these Kolyvagin primes just by working mod P. Okay, so essentially, when there is a big image, the situation is similar to what we had here in the second case, but in that case, any of these characters that appear in the argument, all these alphas, they are all congruent to one mod P, and you can just work mod P to choose your Kolyvagin primes, and the induction argument can be done by essentially computing FP dimensions. So it's largely simplified. It becomes more complex in our study.
Right. Thanks.
So if there are no further questions.
Well, I see. Sorry, I see one question in the chat. Is it possible to construct BDP p-adical function using other methods like Fontaine's phi gamma module model construction? Yeah, maybe such ideas would be relevant in an analog of BDPs in the case when P is inert. So probably one needs kind of more sophisticated p-adical theory to understand BDP's p-adical function when P is inert in K.
Okay, then let's thank Francesc again and sleep well.
Thank you.